There are a number of other questions we can ask about this situation of the ladder sliding down the wall, besides the one that we asked before. Here's another one. I kept the numbers, everything the same. And we'll need what we did before, but now the question is asking, at what rate is the area of the triangle formed by the ladder wall and ground changing then? Then meaning at the time when the base is 12 feet from the house, right? So I put down here what we had already learned from the previous part of the problem. We had figured out, of course, we had the Pythagorean theorem for the relationship between x and y, and at that point when x equals 12, we had found that y was 5, and where dx dt was 5, then dy dt was negative 12. So that's what we had figured out from the previous video. So we may need some of that information for this one, so I'm just going to put it here so we don't have to redo it. Okay, but now this question is asking about something different. This question is asking about the rate of change of the area. So instead of looking at the distances, it's looking at the area of the triangle. So area of a triangle is easy, right? 1/2 base times height. So in this case, the base is x and the height is y. And what this problem is asking us for is it's asking us for the derivative of the area with respect to t, right? The rate of change of the area. It's asking for this when x equals 12 and all the rest of that other stuff, right? So we need to find that out. Now, we have to take the derivative first and then put in the x equals 12 and y equals 5. Why? Because if I put in x equals 12, y equals 5 here, well then I just get a number and the derivative is 0, right? Or if I only put in one of them, then I don't have the information about the rate of change of the other. So that's why you leave that stuff till the end. You take the derivative as pretty general, right? Unless something is constant throughout the problem, you want to make sure that you're taking the derivative with respect to it. If it's changing, it's moving, then it's got a rate of change and we need to know what that is. So here I'm going to do dA dt on the left-hand side. Now notice though, again, now on my right-hand side I've got 1/2 times d dt of xy, but x and y are both functions of t, so this is a product rule one, right? So this would be 1/2 times x dy dt plus y dx dt. Yeah, so I'm getting 0, all right. Okay. It's not changing at all, right? Because x, no, it works. Okay, I did it wrong in my head. So x is 12 and dy dt is negative 12, and then y is 5 and dy dx is 5. Okay, so I have 1/2 times minus 144 plus 25. Okay, so whatever that is. No, I can't add, right? 3, right? So 9, 1. So negative 119 over 2. Okay, I need units. Now, the area, because x and y are in feet, this area is in square feet, so my derivative has to be in square feet per second. Right? So, which actually you can see it here because this is feet and this is feet per second. So it works out either way, whether you look at the units here or if you look at the units here. Okay, so there's actually one more thing I can do with this. I'm sure there's more, but there's one more like standard one. At what rate is the angle theta between the ladder and the ground changing? So there's theta. Let me write that up. So this is somewhat similar to, but not, so never mind what I said, so I'll just shut up now. What rate is the angle theta between ladder and ground changing. All right, let's see what we got. So I need then, and now I can use anything actually, because I just need to know something about theta, right? So I could use sine, cosine, tangent, doesn't matter. You know what? So I'm just going to use x. Fine. So that would be cosine. So why not? So cosine theta is x over 13, right? Because it's adjacent over hypotenuse. So x is kind of going to be, if it was, there's nothing I can do about it, because 5, 12, 13 is not a nice angle. So x equals 13 cosine theta dx dt equals 13. The derivative of cosine is negative sine. So negative sine theta d theta dt. Okay? So that's basically what I have. Now what I need to solve for d theta dt, because it wants at what rate is the angle theta between ladder and ground changing at then. It should say then, right? Because it's always at that particular point. Okay, so I know what dx dt is. Okay, I'm just going to write it out. So I'm going to write it here. D theta dt is minus 1 over 13 sine theta dx dt. Okay? Oh, but I can figure out what sine theta is at that point, right? Because it's just going to be 12 over 13. Okay? At that point, at that time, now I'm just going to use this because I'm going to use the same triangle. That's what's happening at that time. Okay? Obviously, I don't want to put the 12 in there because then I don't have anything to take the derivative of. So I have to take the derivative first. Again, I'm belaboring this point because it's easy to screw it up. Once I'm done with taking my derivatives, then if I want, I can put my stuff on my triangle or my picture if I have to. So if I look at this thing here, sine of theta is going to be 5 over 13 at that particular point. So the sine of theta is in the bottom, so 13 over 5, right? And then what was dx dt? Dx dt was 5. Oh, everything cancels out. I get negative 1. And, okay, theta is in radians, so d theta dt, it's going to be negative 1 radian per second. Yes. So that would be how that's done for that one. So you do have to be careful with this thing, right? We only plug in the numbers once we've taken the derivative.